The science of physics encompasses many fundamental concepts and principles that help us understand the workings of the universe. One of the most awe-inspiring of these principles is light and its role in the cosmos. Light is a unique phenomenon that exhibits both wave and particle properties and is considered the fastest speed in the universe. The speed of light is not just a constant, it is also a fundamental component that determines how time and space interact. Albert Einstein's theories of relativity have shown us that the speed of light is the absolute limit and how this limit shapes the structure of the universe. The nature of light and its speed has attracted the interest not only of theoretical physicists but also of scientists who help us understand how our technologies work in everyday life. First, let's talk about the nature of light. Light is one of the most intriguing and researched natural phenomena in human history. For centuries, scientists have tried to understand the nature of light, and many significant discoveries have been made in the process. The dual nature of light, exhibiting both wave and particle properties, is one of the most fundamental and interesting concepts of modern physics. The wave nature of light was first proposed by Christian Huygens in the 17th century. Huygens argued that light moves as a wave and propagates like water waves. This theory was used to explain behaviors such as reflection and refraction of light. In the 19th century, Thomas Young's double-slit experiment further reinforced the wave nature of light. In this experiment, when light was passed through two narrow slits, it created an interference pattern, a phenomenon that could only be explained by waves. In the 1860s, James Clerk Maxwell developed the electromagnetic wave theory, showing that light is electromagnetic waves. Maxwell's equations revealed that light consists of oscillations of electric and magnetic fields perpendicular to each other. This theory also calculated the speed of light, providing a solid foundation for its wave nature. The particle nature of light, on the other hand, was another significant approach advocated by Isaac Newton. Newton proposed that light consists of tiny particles that move in straight lines. This theory was especially used to explain the phenomena of reflection and refraction. However, the particle theory fell short in explaining wave properties like interference and diffraction. In the early 20th century, Max Planck and Albert Einstein provided new evidence for the particle nature of light. Planck developed quantum theory to explain blackbody radiation, suggesting that light is made up of discrete energy packets called quanta. Einstein used the particle nature of light to explain the photoelectric effect. The photoelectric effect showed that light of a certain frequency could eject electrons from a metal surface, a phenomenon that could only be explained by the particle nature of light. Modern physics accepts the fact that light exhibits both wave and particle properties. This dual nature has been better understood through quantum mechanics. Quantum mechanics suggests that light and other fundamental particles have both wave and particle properties, and these properties emerge depending on the conditions of observation. In 1924, Louis de Broglie proposed that all matter has wave-like properties. This theory demonstrated that particles like electrons could also behave as waves and experimentally verified that electrons could create interference and diffraction patterns. The double-slit experiment is one of the most striking examples of the wave-particle duality. In this experiment, a beam of light is passed through two narrow slits, and an interference pattern is observed on a screen behind the slits. This pattern demonstrates that light propagates as a wave and interferes with itself as it passes through the slits. However, even when the experiment is conducted with single photons, the same interference pattern emerges over time. This phenomenon shows that even individual photons exhibit wave-like behavior and supports the fundamentals of quantum mechanics, which explain quantum superposition and interference. For a long time, light has fascinated scientists with its dual nature, exhibiting both wave and particle properties. Quantum mechanics has taken a revolutionary step in our understanding of this duality and the nature of light. One of the fundamental components of light in the context of quantum mechanics is the photon. Photons are known as the quanta of light and are the elementary particles of electromagnetic radiation. The concept of the photon was first proposed by Albert Einstein in 1905 to explain the photoelectric effect. This effect occurs when light at a certain frequency strikes a metal, releasing electrons. To explain this phenomenon, Einstein proposed that light behaves as packets of energy. These energy packets were later called photons. Photons are massless particles that travel at the speed of light in a vacuum. High-frequency light consists of photons with higher energy, while low-frequency light consists of photons with lower energy. Quantum mechanics helps us understand the wave-particle duality of light. Light behaves as a wave under certain conditions and as a particle under others. This duality is clearly seen in Thomas Young's double-slit experiment. In this experiment, light passed through two narrow slits creates interference patterns on a screen, demonstrating its wave property. However, even when light is sent at very low intensity, the same pattern forms, showing that photons move one by one and the interference pattern forms over time. This proves that photons simultaneously possess both wave and particle properties. Another important feature of photons in the context of quantum mechanics is superposition states. A photon can exist in multiple states simultaneously. This phenomenon forms the basis of quantum computing and paves the way for the development of quantum computers. Additionally, quantum entanglement between photons is a phenomenon where two or more particles become interconnected, and the state of one instantaneously affects the state of the other. This property is one of the fundamental principles of quantum communication and quantum cryptography. Photons also have properties such as polarization. Polarization refers to the direction of the photon's electric field vector. The polarization properties of photons are used in many technologies, especially in optical communication and imaging systems. Polarized sunglasses are coated with materials that allow only components of light with a specific polarization direction to pass through, thus reducing glare. The universe is filled with many electromagnetic waves, both visible and invisible. The electromagnetic spectrum is a range that encompasses all these waves, including various types of electromagnetic radiation with different wavelengths and frequencies. The speed of light is a fundamental constant that determines the propagation speed of these waves in the universe. Let's start with radio waves. These waves have the longest wavelengths in the spectrum. They are used in many fields, from radio and television broadcasts to the communication of our mobile phones. So, the music you listen to on the radio every morning reaches you thanks to radio waves. Microwaves have slightly shorter wavelengths. Have you ever wondered how the microwave oven in your house works? These waves heat your food. Additionally, Wi-Fi connections and radar systems operate thanks to microwaves. Infrared waves are waves that we cannot see with our eyes but can feel. They are used in many areas, from heating devices to night vision systems. On a cold winter day, the pleasant warmth emanating from a stove occurs thanks to infrared waves. Visible light is actually only a small part of the electromagnetic spectrum, but it is the most important part for us. It is the light we can see with our eyes and contains the colors of the rainbow. So, these waves allow you to see the colors of everything around you. Ultraviolet light is the light that comes from the sun and tans our skin. However, be careful, excessive exposure to ultraviolet light can be harmful. That's why using sunscreen is important. X-rays are used for medical imaging. When you get an X-ray of your bones, these powerful waves pass through your body, allowing doctors to see your internal structure. Gamma rays have the shortest wavelengths and highest energies in the spectrum. They are used in cancer treatment and in studying some astrophysical events. Now, let's move on to the speed of light. Light travels at approximately 300,000 kilometers per second in a vacuum. This speed is the highest known in the universe and is usually denoted by the letter c. Why is this so important? Albert Einstein's theory of special relativity states that the speed of light is the highest speed in the universe and that nothing can exceed this speed. This theory helps us understand how time and space work. For example, on a spaceship traveling close to the speed of light, time flows more slowly. Albert Einstein developed the theory of special relativity in 1905, and this theory completely changed our way of understanding the universe. The theory of special relativity is based on a few fundamental principles. The speed of light is constant, regardless of the observer's movement or speed. This means there is an absolute speed limit in the universe. No matter how fast you move, the speed of light relative to you always remains the same. One of the most striking consequences of the theory of special relativity is how time and space change with increasing speed. As an object approaches the speed of light, time slows down for it. This is called time dilation. For example, if an astronaut travels at a speed close to the speed of light, the time passing for them will be much slower than for an observer on Earth. Similarly, as an object approaches the speed of light, its length in the direction of motion shortens. This effect, which arises from the structure of spacetime, is called length contraction. As an object's speed increases, its mass also increases. As it approaches the speed of light, this mass reaches an infinite value. Therefore, it is impossible to accelerate an object to the speed of light, as it would require infinite energy. Let's consider the twin paradox, an intriguing thought experiment of the theory of relativity. The twin paradox describes a situation where one twin travels into space at a speed close to the speed of light, while the other twin remains on Earth. When the traveling twin returns, they are much younger than the twin who stayed on Earth. This situation is a direct result of time dilation. The theory of relativity is not only a topic of interest for theoretical physicists but also has significant applications in our daily lives. For example, GPS systems account for the effects of relativity when calculating the travel time and movement of satellite signals to Earth. This ensures our devices can accurately determine our location. The measurement of space and time is made possible by the speed of light. When measuring vast distances in space, we use the time it takes for light from stars to reach us. For example, light from the sun takes about 8 minutes to reach Earth. Modern technology relies on the speed of light. Internet data is transmitted at the speed of light through fiber optic cables. This enables us to enjoy superfast internet connections and high-resolution videos. Have you ever wondered how we measure the speed of light? Many scientists throughout history have worked on this. Initially, it was believed that light traveled at an infinite speed. However, over time, this notion changed, and scientists began trying to measure the speed of light. In the 17th century, Galileo Galilei made one of the first attempts to measure the speed of light. Galileo and another person positioned themselves on distant hills and tried to measure the time it took for light signals to travel between them. However, it was not possible to measure the speed of light accurately using this method because light was too fast, and the distances were too short. A significant step in measuring the speed of light was taken by Danish astronomer Ole Romer in 1676. Romer observed the movements of Jupiter's moon Io to calculate the speed of light. By using the time difference between Io's closest and farthest positions to Earth, he measured the time it took for light to travel a certain distance. These observations showed that light had a finite speed, and Romer estimated the speed of light to be approximately 220,000 kilometers per second. This value was quite close to the actual value and had a significant impact on the scientific community. In the 19th century, French scientists Hippolyte Fizeau and Léon Foucault conducted experiments to measure the speed of light more precisely. In 1849, Fizeau used a setup involving a rotating toothed wheel and a mirror to measure the speed of light. In this experiment, light passed through the teeth of the wheel, hit a mirror, and reflected back. By adjusting the rotation speed of the wheel, he calculated the speed of light and found it to be approximately 313,000 kilometers per second. Foucault, in 1850, used a rotating mirror for a more accurate measurement and determined the speed of light to be approximately 298,000 kilometers per second. Foucault's method provided a more accurate and reliable result, and this value was very close to the currently accepted speed of light. One of the most precise measurements of the speed of light was made by American physicist Albert Michelson. In 1879, Michelson used rotating mirrors and long distances to measure the speed of light. His work was further refined in 1926, and he determined the speed of light to be 299,796 kilometers per second. This value was very close to the currently accepted value, and Michelson won the Nobel Prize in Physics for his work. Today, the speed of light is measured with much greater precision. Using modern technologies like lasers and atomic clocks, the speed of light has been determined to be 299,792,458 meters per second. This value serves as a basis for defining the meter and is accepted as an international constant. For more fascinating documentaries and scientific content, don't forget to subscribe.